The volume of a cone varies jointly with its height and the square of its base radius. A cone has a base radius of 4 feet, a height of 6 feet, and a volume of 100.48 feet. What is the volume of a cone with a height of 3 feet and a base radius of 3 feet? All right. Now, when we see the phrase varies jointly with, they've given us some important information. First of all, if it varies jointly, we know there's going to be multiple inputs, but they're all going to be related through multiplication because it's strictly direct variation. And when it's the volume that's doing the varying, that means the volume is the variable that's alone. So as I start to set up this problem, I'm going to say that the volume varies directly with, okay, height and square of the base radius. So that's going to be an r squared. So notice these fancier types of variation actually can involve powers. So just be on the lookout for that in the wording. Then they give us a specific example, kind of like when we had that specific point in a previous problem. A cone has a base radius of 4 feet, so this is 4, and a height of 6 feet, and we're told that the volume is 100.48. So as I start to do this, I see 100.48 equals the constant of variation times 6 times 4 squared. Well, we know that 4 squared is 16, and that 16 times 6 is 96. So if we divide both sides by 96, then our constant of variation is approximately equal to 1.047. It's more accurately equal to 1.046 repeating. That would be not rounded. So when it then asks us to find the volume of a cone, we need to use this constant of variation. We need to put that right here in for the constant. So I'm going to say that the volume of the cone is this number times the 3 feet for height and the base radius of 3 squared. Now, conveniently, I still have that number, that 1.046 repeating in my calculator, so I'm just not going to retype it. I'm going to, in my calculator, tell it times 3 times 9, because we know that 3 squared is 9. So I'm just taking this decimal that's already in my number, and I'm multiplying it by 27. When I do that, I can see that the volume is equal to 28.26, and that's actually exact. Since I didn't round my number off, I can trust that when that number comes out to actually only have 2 decimal places, that is in fact accurate. And so that's going to be feet cubed. So that's actually the answer that they're looking for. Our last word problem says that the volume of a gas varies directly with its temperature and inversely with pressure. So this is an example of combined variation because we have 2 different types of variation in the same problem. So again, the volume is what's doing the varying. So volume is alone on one side of the equal sign. It's varying with some constant that we don't yet know. It's varying directly with the temperature and inversely with the pressure. So now I have a basic template, and I'm assuming that they're going to give me a specific scenario where we know all 3 of these variables, because then that will enable us to find out what the constant of variation is. And lo and behold, that's what comes next. The volume is 100 when the temperature is 150 kelvins and the pressure is 15 pounds per centimeter cubed. Well, 150 divided by 15 would just be 10. And if we divide both sides by 10, we can see that the constant itself is actually equal to 10. So the actual specific model is that the volume equals 10 times the temperature divided by the pressure. So now it asks us, what is the volume when the temperature is 250 kelvins and the pressure is 20 pounds per centimeter cubed, per centimeter squared. So again, I can cancel. I've got 250 divided by 2 is 125. So that's going to be 125 meters cubed.